Today we are going to discuss physics problem 34. Statement of the question is already on the board. There are two masses A and B. A is supported by two strings making 37 degree to the horizontal ceiling. B is in equilibrium supported by two springs also making the same angle 37 degree, equal length, making 37 degree with the ceiling. So at a certain instant, this left string of A and the right string of A and the right string of B are snapped, means cut off. At a certain instant, this string and this spring are cut off. So equilibrium is disturbed by that. So both A and B will start moving. A and B will start moving with two different accelerations. The reason I will tell you as we proceed. The ratio of the two accelerations is what we want. So in this respect, the basic difference between a string and a spring you should understand first. When one string is cut, the tension, one string is cut. This is the diagram after string is, the right string is cut. Immediately the tension in the string will change in order to satisfy the situation after cutting the string. This tension will immediately change. Whereas this is not the case with a spring. Spring's tension is associated with some elongation. Considerable elongation is there. Till that elongation becomes zero, the spring will try to maintain some tension. It will try to maintain. So immediately after cutting, the tension will be the original tension only. The spring tension will remain as original tension. This tension will change. So first we find the original tension. Original tension is the tension that is balancing the weight of this mass, equal mass only. So P cos 30 degree, cos 53 degree, P cos 53 degree, P cos 53 degree is the component of P in the vertical direction. There are two tensions, so 2T, this is equal to mg. So let me complete that. 2T times cos 53 degrees, 3 by 5 is equal to mg, giving us tension, original tension is equal to 5 mg by 6. 5 mg by 6. So now let us see how the tension changes in the case of string. Immediately after cutting that, this A will have the weight of this mg will try to pull A downwards like this. This angle is 37 degree also. So mg sin 37 degree. Mg sin 37 degree will be acting this way. It will tend to pull this downward like that, but tension will change. Immediately change to, from this value, it will change to another value, same. That is, this mg sin 37 degree will be balanced. So that parallel to the string, this mass cannot move. So this tension changes. This is mg, means 3 mg by 5. 3 mg by 5. So tension from 5 mg by 6, it changes to 3 mg by 5 immediately. Whereas this is free to move at right angle to the string. So right angle to the string, tension is mg cos 37 degree, which is 4 mg by 5. 4 mg by 5. So that in this direction, this is free to move. So it will have acceleration corresponding to this. No acceleration in that direction. Whereas the case is different with the case of the spring, it is a different case. So we shall discuss that. Now, before I proceed further, I will delete this statement so that we will have enough space for further discussion. Now, let us see the situation with the spring. Spring, this weight component will be still there, mg sine 37 degree, which is 3 by 5 mg. Original tension will still remain because string has to come to its natural length before it loses the tension. So immediately after cutting, the original tension, which was 5 mg by 6, is still there. 5 mg by 6. So parallel to the string or spring also, this mass will have some acceleration, and normal to the string, the same regular acceleration, which is same as for both, same acceleration. This 4 mg by 5. It will be the force component, weight component in this direction. Because mg is acting down, this mg also acting down. So parallel to the string, this component, normal to the string, this component. So now we have to calculate two accelerations for this one. So I will draw the spring case again for clarity purpose. Ceiling being this, spring is like this. It has acceleration in this direction is you divide by m, 5g by 6. Acceleration in this direction is divide by m, you get 3g by 5. Acceleration in this direction is divide by m, you get 4g by 5. So parallel acceleration A parallel for the spring mass is A parallel is this 5g by 6 is larger, 3g by 5 is small. So it will have a parallel acceleration in this direction, upward direction, equal to A parallel is equal to A parallel equals 5g by 6 minus 3g by 5 equal to 7g by 30. A normal, this is the normal acceleration, A normal acceleration is 4g by 5. So it is the resultant of these two will be the acceleration of the related to the spring, this mass attached to the spring. So we find the resultant acceleration of A is only this 4g by 5. Acceleration of B square is equal to 7g by 30 square plus, because both are at right angles, plus 4g by 5 right angles square. So the required ratio is this is this implies A is solution of A is 4g by 5. Acceleration of B is square root of this, the acceleration. So From that you have to get the ratio. So I will continue this. Acceleration ratio is given by acceleration ratio this is already in the square form, so I will take it as AB square by AA square is equal to 7g by 5 by 30 square plus 4g by 5 square divided by square of, because both is A also you have to add in the square form, so represent in the square form 4g by 5 square, which gives us the square as 7 by 30 times 5 by 4 square plus 1, which also reduces to 7 by 24 square plus 1, which is equal to 25 by 24 square, because 24 square by plus 7 square is 25 square, so 25 by 24 square. So that is what we get. Now we express the final answer to the question as final answer we express, because when questions are asked, we must keep to the same order of items. So same order of item means AA by AB is what we want. So that will be equal to 24 by 25. So B with mass attached with the spring is having a slightly larger acceleration because of the tension prevailing in the spring even after cutting one spring. So I think you can follow the solution. Thank you.